Hello students. So here we are with the lecture 5 of Haloalkanes and Haloarenes. Optical isomerism in halogen derivatives. Chiral atom and molecular chirality. So sp3 hybridized atom in a molecule which carries 4 different groups is known as the chiral carbon. The carbon which is attached to the 4 different groups. Carbon is tetrahedral and its 4 valencies are satisfied by the 4 different groups that it is called chiral carbon. It is represented by the asterisk mark, and the other names for this is asymmetrical carbon, stereo center, chiral center. Okay, this does not have plane of symmetry. What do you mean by plane of symmetry? That means this cannot be divided into two equal halves. This carbon cannot be divided into two equal halves, and it forms non-superimposable mirror image. So if you see the mirror image of this carbon, you see here it is non-superimposable. So if you put the mirror and object and mirror image one over the other, it is non-superimposable. So they are called enantiomers. And one of them is known as dextrorotatory, another is known as levorotatory. Dextrorotatory is represented by small d and the plus sign, or it is levorotatory is represented by small l and the minus sign. Here, so what is chiral carbon? The sp3 hybridized carbon which is attached to 4 different groups is called chiral carbon. And these carbons do not have plane of symmetry. They cannot be divided into two equal halves, and they form non-superimposable mirror images. So these object and non-superimposable mirror images, their relationship is known as enantiomers. So one is dextrorotatory, that rotates the plane polarized light in the clockwise direction, and another is known as levorotatory, that rotates the plane polarized light in the left anti-clockwise direction. And this is dextrorotatory is represented by small d and the plus sign, and levorotatory is represented by small l and the minus sign. Clear? Okay. Now optical isomerism. What is this optical isomerism? The stereoisomer in which the isomers have different spatial arrangement of atoms or groups across the chiral carbon is called optical isomerism. So stereoisomers that show different spatial arrangement of atoms or groups around the chiral carbon are called optical isomers, and this phenomenon is called as optical isomerism. And they rotate the plane polarized light in the opposite direction. These isomers, they rotate the plane polarized light in the opposite direction. Now, what is plane polarized light? The normal light, the monochromatic light having single wavelength, vibrates in all the direction. Okay, such a normal light, when it is passed through the Nichols prism, which is polarizer, which is having slit parallel to one of the directions of the light. So when this light is passed through this polarizer, through Nichols prism, then the radiation which is parallel to the slit only passes. And this light having a unidirectional unidirectional oscillation is called plane polarized light. So this Nichols prism is made up of calcite crystals and is also called a polarizer. So this light that comes out from the polarizer is called plane polarized light. Here you see the when ordinary light passes through the Nichols prism, the transmitted light oscillation is only in one plane perpendicular to the propagation of light. And this light is known as plane polarized light. Clear? Okay. So the property of the light to rotate the plane polarized light in right direction or left direction is called optical activity. And such compounds which rotate the plane of plane polarized light are called optically active compounds. So here you see the normal light when it is passed through the polarizer, the oscillation that is parallel to the slit passes by, and this light is called plane polarized light. And when this plane polarized light is passed through the sample tube that contains the organic compound having chiral carbon, then they rotate the plane polarized light in the right hand direction or in the left hand direction. If it rotates in the right hand direction, it is called dextrorotatory, and when it rotates in the left hand direction, it's called levorotatory. So those which do not rotate the light they are called optically inactive. So the angle through which they rotate the plane polarized light on passing through it is called optical rotation, and according to the optical rotation, an optically active compound is dextrorotatory or levorotatory. So if the value is in plus clockwise direction, it is dextrorotatory, and if the value is in negative, then it is called opposite direction. When it rotates in the anti-clockwise direction, then it is called levorotatory. So dextrorotatory compounds are those compounds which rotate the plane of plane polarized light towards right hand direction or the clockwise direction. It's called dextrorotatory. It is represented by small d or plus. And levorotatory compounds are those that rotate the plane of plane polarized light towards left hand side anti-clockwise direction and is called levorotatory compound. It is represented by small m or minus. And these dextrorotatory and levorotatories are mirror images, non-superimposable mirror images of each other. For example, if you take lactic acid, here this carbon of the lactic acid is a chiral carbon because 4 different groups are attached to it, and when you see the mirror image of it, it forms non-superimposable mirror image. That means these are optical isomers and they show optical activity. One of them is known as dextrorotatory lactic acid and another one is known as levorotatory lactic acid. Here another example is 2-chlorobutane. So 2-chlorobutane also, if you see the mirror images, they are non-superimposable mirror images, and they also, one of them is known as dextrorotatory and another one is known as levorotatory, depending on the rotation of the plane polarized light towards left hand side or towards right hand side. If they rotate towards left hand side, they are called levorotatory, and if they rotate the plane polarized light in the right hand side or a clockwise direction, it is called dextrorotatory. Clear? Okay. Now enantiomers. So what are enantiomers? Optical isomers which are non-superimposable mirror images of each other and which rotate the plane of plane polarized light in same angle but in opposite direction are known as enantiomers. So these enantiomers have identical physical properties like melting point, boiling point, densities, refractive index, except the sign of optical rotation, but they have same chemical properties except towards the optically active reagent. Clear? Okay. Now, if you mix this dextrorotatory and levorotatory, if you prepare a mixture, an equimolar mixture of the two enantiomers of D and L, they will be optically inactive. Why? Because one is rotating the plane polarized light in the right hand direction, another is rotating in the left hand direction. So their optical rotation gets cancelled, and due to the external compensation, the mixture is optically inactive. So how do you define the racemic mixture? It is the equimolar mixture of the enantiomer, dextro and levo compound, which is optically inactive due to external composition, and it is called racemic mixture. Okay, and it is designated as DL or plus minus in the bracket. Okay, got it? Now, optical activity of 2-chlorobutane. This question is asked in the boards. Explain optical activity of 2-chlorobutane. If such a question is asked, how do you write the answer? First, write the formula of 2-chlorobutane. So then you say this 2-chlorobutane contains what? Asymmetric carbon or the chiral carbon to which 4 different groups are attached. So which 4 different groups are attached here? Methyl group is attached on one side, H is attached, then CH2CS, that CH3, that is the ethyl group is attached, and the chloro group is attached. So because 4 different groups are attached to this carbon, this 2-chlorobutane carbon is known as chiral carbon. Okay, then number of isomers it will form depends on the number of chiral carbon it possesses. So this is calculated by the formula 2 to the power of n, where n is the number of the asymmetric carbon or the chiral carbon atoms. So in this particular example, how many chiral carbons are there? One chiral carbon of there. So how many isomers it is forming? 2 to the power of n is equal to 2 to the power of 1 is equal to 2. That means these two isomers are the pair of enantiomers that form non-superimposable mirror image over of each other. Clear? So it forms how many isomers? Two isomers. And they are the mirror images of each other. So here you see this is the object and this is the mirror image. So what is differing in these two object and mirror images? The position of H and Cl. So this B, if you place it over A, there will form the non-superimposable mirror image. So one of them is represented by plus chlorobutane, another one is represented by minus chlorobutane. And chlorobutane can exist in two different forms, D form and L form, which are non-superimposable mirror image of each other. So D form rotates the plane polarized light towards the right hand direction, while L form rotates the plane polarized light towards the left hand direction. Clear? Now, equimolar mixture of D and L forms a racemic mixture, and that is optically inactive, and this inactivity arises due to external compensation. Clear? So, then representation of the configuration of molecules by the Fischer projection formula. So, if you have to represent the through Fischer projection formula, and this is the wedge formula. So in the wedge formula, what do you see here? This is the chiral carbon to which four different groups are attached: bromine, chlorine, hydrogen, and iodine. Okay. So in this you see this carbon, bromine, and carbon, chlorine. They are in the plane. This is above the plane H, and this I is below the plane. So above the plane is represented by the wedge solid line and below the plane is represented by the dotted line. Clear? So if you have to convert this wedge formula to Fischer projection formula, in Fischer projection formula you represent the bonds by the cross. Okay. So here you see in the plane, and here you see this I and Br are above the plane and bonds below the plane. This H and Cl are below the plane. So below the plane is represented by the vertical line, and above the plane are represented by the horizontal line. So that's how you below the plane is represented by the vertical line. Okay, and above the plane are represented by the horizontal line. So that's how you will convert the wedge formula to the Fischer projection formula. The cross formula is known as the Fischer projection formula. How do you perform the laboratory test for the haloalkanes? How do you, if in a test tube compound is given, how will you come to know that it is a haloalkane? So in this alkyl halide you reacted with NaOH or potassium hydroxide, you get alcohol plus halide ion is formed. This halide ion, when reacted with dilute HNO3 and AgNO3, the silver halide is precipitated, and that's how you come to know the presence of halogen in the organic compound. Thank you.